Divide and conquer is an algorithm design paradigm where we break a problem down into smaller subproblems, solve those subproblems recursively, and then reassemble the solutions in order to solve the original problem. Over the next few classes, we'll see a number of examples of divide and conquer algorithms, but it's likely that you've seen some divide and conquer algorithms before. So today we're going to demonstrate how we can prove correctness and analyze running time for divide and conquer algorithms using the familiar example of merge sort. As a reminder, the merge sort algorithm sorts an array recursively by splitting the array into two halves and calling merge sort on each half. And then, when it gets back the two sorted half arrays, it performs a merge step to combine them into a single sorted array. The base case of the recursion happens when we get to an array of length less than or equal to 1, at which point we know that the array is already sorted. And when we perform a merge, we are calling a function that assumes the two halves of the array are already in sorted order. Then we have a loop that on each iteration looks at the first element in each of the two halves of the array and picks whichever one is smaller to put into the ith position. When reasoning about divide and conquer algorithms, a natural technique for proving their correctness is an inductive proof where the induction in the proof mirrors the recursion in the algorithm. So if we wanted to write such a proof for merge sort, then the first step would be to prove that our merge algorithm is correct. And to prove the correctness of the merge algorithm, we would show that if we are given an array that meets the precondition, which is that both the left and right halves of the array are already sorted, then when we get to the end of the loop, we have an array that is fully sorted. And for our purposes today, we will take as given that we have already proven the correctness of merge. And now we have to argue that our recursive merge sort function will correctly sort an array of any size. That proof operates by induction on the size of the input array. So the base case is the smallest arrays that we care about, and the base case of the recursion can match the base case of the algorithm. Our algorithm stops recursing when we get to a length of less than or equal to 1. So a length 0 or 1 array can give us the base case for our induction. And just like we have an almost trivial base case to our algorithm, where all we have to do is recognize when we're done recursing, we have an almost trivial base case to our proof, because a length 0 or 1 array is always already sorted. So now we know that when we call merge sort on an array of length 0 or 1, the result is a sorted array. And now we want to proceed inductively, thinking about what happens when we call merge sort on an array of length n, where n is at least 2. And our inductive hypothesis is that the algorithm works on smaller arrays. We're going to try and prove that merge sort works on arrays of length n, and we are assuming that for any length less than m, merge sort is correct. And what that allows us to do is to assume that the recursive calls that operate on smaller arrays will give us back correctly sorted subarrays. So now we know that when we call merge sort on the left half and the right half of the array, the left and right halves will come back sorted, and that meets the precondition that we stated for the correctness proof of merge. And so because merge is correct when given an input where the two halves are already sorted, we know that the result of this merge call will be that the array comes back sorted. And so apart from the detail of filling in the correctness of merge, that's all there is to our correctness proof for merge sort. So relative to other types of algorithms we've seen, proving the correctness of divide and conquer algorithms can often be quite manageable because the structure of the proof so closely mirrors the structure of the algorithm. But of course there's a catch, which is that analyzing the running time of divide and conquer algorithms can be quite involved. The basic idea for analyzing divide and conquer running time is to write down a recurrence relation that describes the running time of the algorithm as a function of the running time on smaller subproblems. And that description, again, very nicely matches the structure of the algorithm. But at this point, we have a recurrence relation to solve, and that can get tricky. We'll talk about a couple of different methods for solving recurrence relations, but first we need an example to work with, so let's come up with a recurrence that describes the running time of merge sort. We'll describe the running time of merge sort with a function m that depends on the input size n. And when we run merge sort on a size n array, we will split into two arrays of size n over 2 and call merge sort on those. So the running time of the outer merge sort includes two calls to merge sort on smaller arrays. Technically, the size of those arrays might be the floor and ceiling of n over 2 because there's potential rounding. And we dealt with that rounding in our proof of correctness by having the two base cases for size 0 and size 1 arrays. But in analyzing the running time, we'll make our lives easier by assuming that n is always a power of 2, so we can divide it by 2 as many times as we need to and still have a clean-looking recurrence. So when we run a call to merge sort, in addition to twice the time of the half-size call to merge sort, we also need to add in the time to perform a merge. The merge function starts with a linear time copy operation. Then it has a for loop that runs once for every element of the array. The body of this for loop has lots of comparisons and copies, but will take constant time. And so the running time of merge is the linear time for the copy plus the linear time for the for loop, so we get some constant times the size of the array. And we'll call that constant C1 because we're about to need an additional constant. And that second constant comes from the base case because we also need to describe that running time to give us a base case for the recurrence relation. When we get to the base case of our algorithm, we no longer have these calls to merge sort and merge. We will skip over the if statement and simply return, which takes some constant amount of time. So we'll describe the base case running time as C2. So now our recurrence describes the running time on a size n array as depending on the running time for a size n over 2 array whenever n is at least 2. And we have a running time that is constant when we get to the base case where n is less than 2. So our recurrence relation that describes the running time nicely corresponds to our merge sort algorithm. We have two calls to the recursive function, and so we pay twice the running time of the function call on an input of half the size. But unfortunately, this recurrence relation doesn't give us a functional description of the running time that we can do big O analysis on. Instead, we have to solve this recurrence to figure out a functional form that we can do big O analysis on. And we'll talk about two different techniques we can use for solving this recurrence. The first is to draw a recursion tree, and the second is to use partial substitution. And we'll go through an example of each of these techniques using our merge sort recurrence. In the tree method for solving the recurrence, we're going to draw a tree whose nodes correspond to the various calls that we make over the course of the recursive algorithm. And in each node, we will denote the amount of work being done by that particular call, excluding the work that is done by the recursive calls and only counting the work that is done at that particular level. So in our recurrence, 2 times m of n over 2 was describing the work in the recursive calls, and c1 times n was the work being done actively at this level by the call to merge. So at the top level of our tree, we have a single node for when we called merge sort on the entire array, and at that level, we have c1 times n, where the size is the entire array. When we go one level down, we're now thinking about the first recursive calls to merge sort, and each of those operates on an array of size n over 2. So when we evaluate the c1 times n term of the recurrence, n on those recursive calls will be n over 2 from the original array. So in each of these nodes, we do c1 times n over 2 work performing a merge, and each of these nodes recursively calls merge sort, and so we extend our recursion tree. And this will proceed down the levels of the tree, where at the next level we will be operating on arrays of size n over 4, and so on, until we get to the bottom, where at the second to last level we have arrays of size 2, and then at the very last level we have arrays of size 1. But when we get to that base level, we are no longer doing split and merge operations. We're instead doing the constant amount of work described by C2. So this tree now illustrates the total work that is done by the merge sort algorithm. And so our task is to add up over all of the nodes in this tree how much work is being done at each node, and that overall will give us the total work done by the entire algorithm. At the top of the tree, we are at level 0 of the recursion, and there is one node where we are doing c1 times n total work. When we get to level 1 of the recursion, we have 2 nodes that each are doing c1 times n over 2 work. And when we add up the total work done across all of the nodes at this level, we have 2 nodes, each operating on half the array, and so the total amount of work is c1 times n. This continues with 4 nodes, each operating on a quarter of the array. And when we get down near the bottom of the tree, we will, at this level, have n over 2 nodes that are each doing 2 times c1 work. And so again, we have c1 times n total work being done. Then at the very bottom level, we will have n different base case nodes, where at each of those nodes we're doing C2 work. And now our goal is to add up the work done across all of the levels to figure out the total amount of work done by the algorithm. And since at every level but the last we are doing C1 times n amount of work, we simply need to figure out how many levels there are, and then we can multiply that by C1n. Well, if we started from an array of size n at the top and split it in half every time, we get to arrays of size 1 after log base 2 of n levels. So from level 0 to the second to last, we have log base 2 of n levels, and we add up the total work across those levels. And then we can add the work done at the last level. And we get a total amount of work that is big O of n log n. When analyzing other algorithms, we might not have this nice alignment where the same total amount of work happens at every level. And in that case, we would need to figure out how much work is done at the level as a function of the level number, and then that expression in terms of I could go inside this sum, and we might have a more involved solving of the sum to get to our big O result. The second approach that we'll consider to solving running time recurrences is known as the substitution method. And the goal of the substitution method is to prove inductively an upper bound on this recurrence. The starting point for substitution is to have some guess as to what type of function we think might give us an upper bound on the recurrence. And in this case, since we just used the tree method to find that the recurrence is big O of n log n, we can start with the guess that this recurrence is upper bounded by some constant times n log n. When using the substitution method, we start by guessing some function that we think will give us an upper bound on the recurrence. And we go for an upper bound because we know we're going to do big O analysis in the end anyway. But we don't have to specify that function exactly. We can leave some details of the function, like this constant k, unspecified. And in the course of constructing an inductive proof that m is less than k times n log n, we will figure out what value of k we can pick that will make the proof work out. And so in the end, we will have a more specific function that we have proven upper bounds m. Our inductive proof aims to show that this upper bound holds for all positive integers n, and so we start our induction with a base case of the smallest input we care about, which is n equals 1. And if we plug in n equals 1 to our upper bound formula, we get a value of 0, and no matter what k we pick, it will not be the case that k times 0 is larger than m, and so we've already messed something up. We cannot prove that this upper bound holds for all positive integer values of n. So what can we do about this? Well, we have several options. One is that we could change our guess. We think that there is a big O of n log n function that will upper bound m, and we could pick a different function that is still big O of n log n. For example, we could add some constant to our upper bound function. And when we do big O analysis in the end, that constant will go away and we'll still get n log n. Or we could take advantage of the fact that big O only requires the bound to hold as n goes off to infinity. And so we could change our base case to, instead of starting from 1, we could start from a larger value of n. And if we prove that from that point forward the upper bound always holds, then we can still do big O analysis, because it's okay to have some exceptions for small values of n as long as our upper bound holds as n goes off to infinity. For this proof, I will take the latter approach and change our base case to be n equals 2. And to show that this upper bounds the recurrence, we need to evaluate what does our recurrence give us when n equals 2. Evaluating our recurrence at n equals 2 depends on our recurrence at n equals 1, but at the base case, our recurrence gives us c2, and so we get 2 times c1 plus c2, and to prove that this upper bounds this, we now have a constraint on what value of k we can pick. So we said that we would fill in the value of k as we went, and we now know that k has to be at least c1 plus c2. Now that we have our base case, we want to do an inductive step where we assume that our upper bound holds for smaller values of n and show that that implies it will hold at n. To show this implication, we hypothesize our if and try to arrive at our then. That means our inductive hypothesis is this. So let's express our recurrence evaluated on n and try to give it an upper bound. Since we're thinking about some value of n that is bigger than our base case, we know we are in this case of the recurrence. And notice that because we have m evaluated on n over 2, which is less than n, we can use our inductive hypothesis to substitute an upper bound for the running time on n over 2. And now we proceed to simplify. We can cancel the 2's, and we can use log rules to split up log of n over 2. And since log base 2 of 2 is 1, we can simplify and distribute the k times n. And now we can group up the linear terms. And our goal was to show that m is less than or equal to k n log n. And we have k n log n plus this term. So we need this term to come out negative. And that will happen as long as k is at least c1. And now we've reached our desired conclusion. So as long as k is at least c1, we know that k times n log n will give us an upper bound on m for every n that's at least 2. Along the way, we imposed two different constraints on k. And since C1 and C2 were both describing some amount of computation, they are both positive numbers. So, to satisfy both the constraints that k is at least C1 and k is at least C1 plus C2, we can just choose k to be equal to C1 plus C2. So our guess started with an unknown value of k, but we've now figured out a value for k that makes the proof work. And so we've proven that this function is an upper bound on the recurrence, and that means that the recurrence is big O of n log n.